When you type a URL and press enter, the browser begins downloading an HTML document, but contrary to what many people imagine, the browser doesn't wait for the entire document to arrive before it starts rendering. HTML arrives over the network as a stream of bytes, often in multiple chunks. As soon as the first bytes arrive, Blink immediately begins parsing and building internal data structures. The first component that touches these bytes is the HTML tokenizer. Its job is to transform a raw stream of characters into meaningful tokens, such as start tags, end tags, attributes, and text nodes. The tokenizer itself is an enormous state machine with dozens of states defined by the HTML specification, including data state, tag open state, script state, comment state, and many more. As tokens are produced, they're fed to the HTML tree builder. The tree builder constructs the document object model, or DOM. Every HTML element becomes a C++ object inside memory. A div becomes an HTML div element, a paragraph becomes an HTML paragraph element, and text becomes text nodes. The DOM is constructed incrementally as data arrives over the network. At the same time, CSS is also being downloaded and parsed. CSS doesn't remain as plain text. The browser tokenizes it and builds internal rule structures that allow selectors to be matched efficiently. Rules such as .card or div greater than span are transformed into highly optimized lookup structures. Once both the DOM and CSS rules exist, Blink begins one of its most expensive operations, style calculation. Every element in the document needs to know exactly what its final styles are. To do that, the browser runs the entire CSS cascade. The cascade takes into account browser default styles, user styles, author styles, selector specificity, inheritance, CSS variables, animations, transitions, and even the order in which style sheets were loaded. The final result is a computed style object attached to every element in the document. Importantly, the browser tries very hard to avoid recalculating styles for the entire page. If you add a class to one element, Blink performs style invalidation. It asks a series of questions. Which selectors could be affected? Which descendants inherit from this property? Which ancestors need to be revisited? Only the necessary parts of the tree are recalculated. At this point, many people assume that the browser directly lays out the DOM tree. It doesn't. Blink constructs another tree entirely dedicated to rendering and geometry. This is called the layout tree. The layout tree contains only renderable objects. Elements with display none don't exist inside it. A div might become a layout block flow object, text becomes layout text, images become layout image, and tables have their own specialized layout objects. Modern Blink goes one step further and creates something called a fragment tree. This exists because layout is no longer as simple as assigning a single rectangle to an element. Content can break across lines, columns, pages, and regions. A single paragraph may generate many fragments distributed across multiple containers. Then comes one of the most expensive phases in the entire pipeline, layout, also called reflow. The goal of layout is simple to describe, but incredibly difficult to implement. The browser needs to answer 4 questions for every single element. How wide is it? How tall is it? Where is it positioned? And how do its children fit inside it? To perform layout, Blink passes around structures called constraint spaces. These represent the amount of available space an element can use. For example, if a parent has a width of 800 pixels and a child has width 50%, the child computes its width as 400 pixels. Unfortunately, real websites are far more complicated than this. Widths can be auto. Heights can depend on content. Flexbox and grid often require multiple layout passes. Some elements depend on the sizes of their siblings. Others depend on their descendants. The browser is effectively solving a large geometric constraint problem. Text layout is particularly difficult. When the browser sees a piece of text, it can't simply count characters. It needs to determine font metrics, glyph positions, kerning information, ligatures, language-specific shaping rules, bidirectional text handling, and fallback fonts. For this, Blink uses Harfbuzz, a sophisticated text shaping engine. Harfbuzz transforms Unicode text into positioned glyphs. The word office, for example, may contain an phi ligature represented by a single glyph rather than 3 independent characters. After shaping text, the browser performs line breaking. Given an available width, it decides where words wrap and generates line boxes that represent the final arrangement of text on the page. Absolute positioning adds another layer of complexity. An absolutely positioned element must determine its containing block, which may be its parent, an ancestor with transforms, or even the viewport itself. Only after that can the browser compute its final coordinates. Once layout finishes, the browser knows the geometry of every renderable object, but surprisingly, we're still nowhere near pixels. The next phase is called pre-paint. This stage exists because modern rendering involves much more than simply drawing rectangles. During pre-paint, Blink computes paint invalidation information, clipping relationships, scrolling information, visual effects, and compositing inputs. One of the major outputs of pre-paint is a set of structures called property trees. Instead of storing transforms, clipping, scrolling, and effects directly on every element, Blink builds specialized trees for each concern. The transform tree stores transformation matrices. The clip tree stores clipping regions. The scroll tree stores scroll containers. The effect tree stores opacity filters and blending information. These trees dramatically reduce the amount of work needed during rendering. After pre-paint comes paint. The word paint is somewhat misleading because the browser still doesn't generate pixels here. Instead, Blink records drawing instructions. A red background becomes a drawRect command. Text becomes a drawText command. Images become drawImage commands. These commands are stored inside a display list, essentially a sequence of instructions describing how the page should eventually be drawn. The browser then decides which parts of the page deserve their own composited layers. Not every element gets a layer because layers consume memory and GPU resources. Properties such as transforms, opacity animations, videos, canvases, and fixed positioned elements often receive dedicated layers. The result is a layered tree that can be manipulated independently of the rest of the page. At this point, rasterization finally begins. Rasterization is the process of converting display commands into actual pixels. Chromium uses the Skia graphics library for this task. Skia executes commands like drawRect, drawText, drawPath, and drawImage and generates bitmaps containing raw RGBA pixel data. However, modern web pages can be enormous. Some pages are tens of thousands of pixels tall. Rasterizing the entire page would consume enormous amounts of memory, so Chrome divides layers into tiles, often 512 by 512 pixels. Only the tiles that are visible, or likely become visible soon, are rasterized. This process occurs on dedicated raster worker threads, rather than on the main thread. Once a tile has been rasterized, its bitmap is uploaded into GPU memory as a texture. Depending on the platform, this upload may happen through OpenGL, Vulkan Metal, or DirectX. The compositor thread now has everything it needs. It has textures, transformation matrices, clipping information, and effect properties. Importantly, it can manipulate many of these properties without involving the main thread at all. Every frame, the compositor constructs draw quads that describe which textures should be drawn and where they should appear on the screen. These commands are sent to the GPU process, which submits them to the graphics driver. The GPU executes the commands, composites all the layers together, swaps the front and back buffers, and finally the display hardware scans out the finished frame to your monitor. The pixel that ultimately reaches your eyes has gone through an extraordinary journey. It began as a few bytes arriving from the network, became tokens, then DOM nodes, then computed styles, then layout objects, then fragments, then display commands, then rasterized textures, and finally photons emitted by your screen. This entire pipeline repeats continuously as you scroll, click, animate, and interact with the page. Modern browser engines are not simply HTML renderers. They are massively parallel layout engines, graphics engines, and operating systems dedicated to producing millions of pixels every second.